Okay, test. Okay, so let's start. Today is actually our last lecture, and we won't have a lecture on Friday. And this is a special lecture. We are going to have, instead of learning new knowledge, we are going to have a recap of what we have learned this term. And have you done your assignment two? Oh, sorry, quiz two? Yes or no? You should have you should have try at least have a look because the deal is next Friday. So okay, let's start today's lecture. And if you click on this link here, and you will see okay, it seems to be an error here for this the slides today. But that's only because the the website I used doesn't allow to be embedded as an iframe in other web pages. So you just click on this view in browser and you can view it properly. So today we are going to have a recap of what we have learned for the entire term. So okay, let's get started. So this is actually an overview of all the concepts we have learned in this term. And if we zoom in, we can see that we started from the introduction to software testing. And in this introduction, we learned several concepts. The first one is software dependability. So let's see if you can still remember these concepts. So software dependability is like the ultimate goal we want to have, right? So we want to build dependable software. And dependability is consists of four different properties: correctness, reliability, safety, and robustness. And can you still remember the relations between these four properties? Like what is correct but unreliable? What is safe but not robust? So these are the key concepts here. And we also learned the concepts of verification and validation. So in in plain text, they are related to they are related to are we building the product right and are we building the right product? So can you still remember which one is which? So what is are we building the product right? Is it verification or is it validation? Are we building the correct product right? Is it verification or validation? It's verification. And are we building the right product is validation. So verification is more like thinking from the engineer's point of view about the quality of the software. And validation is more like thinking from the user or the customer's point of view about the quality of the software. So are we building the right product is more like thinking from the angle of customers. So let's continue. We also learned two concepts. So dynamic analysis and static analysis, right? So most of the testing techniques are static or dynamic. Can you still remember that? So the testing techniques we are using, like the fuzz testing we are doing for assignment 2, is it dynamic or is it static? It's dynamic, right? Because we need to execute the program. We need to let it execute. We need to run the program. So it is dynamic. And dynamic technique is more about executing the software and observe for abnormal behaviors. And static analysis is more about we scan for certain vulnerable patterns inside the program. So these are the two concepts here. And we also learned 6 basic principles for doing testing. And actually, all these principles, we can somehow see the usage of these concepts in the actual techniques we have learned. For example, for sensitivity, we want to have high sensitivity for detecting bugs, right? So that's why when we design test oracles, we need to think about this problem here. And for visibility and observability, we learned different coverage metrics, right? These coverage metrics can help us to know the progress of our testing, right? And in your assignment two, you also tried to report the coverage of the fuzzer, right? And this is like a show of the progress of the entire fuzzing session. So this actually improves visibility and observability. And that's all about introduction to software testing. And after that, what did we learn? We learned functional testing, right? So functional testing is also known as black box testing. And black box testing means that we know nothing inside the program, right? We don't know what's happening inside the program. We just treat it as a black box. And because we are treating the program as a black box, what we can only control is about the program inputs, right? We only know what are we feeding into the program. And because the input space of all these programs is like infinite. So we can actually feed any type of inputs or any input into the program. So the key idea or the key mechanism of all the functional testing techniques are to divide the input space according to certain rules. And the first rule or the first type of division technique we used here for functional testing is to use the boundary values to divide the input space, right? So that gives us the technique of boundary value testing. And for boundary value testing, we learned two key concepts that gives us variations of different boundary value testing techniques. So the first concept is about whether the testing is normal or robust, right? So normal means that we only care about the cases where there's no value outside the valid region or the valid range of the parameters. And for robust, we care about the invalid inputs, right? And the second characteristic here is about whether do we consider the worst case scenario or not. So this is based on the single fault assumption. And if we have this single fault assumption, it means that at most one parameter can take invalid values, right? And if we break this assumption, it means that more than one parameters can take invalid values. So, and that is like the worst case we can have, right? So, we can have different variations based on these different characteristics of boundary value testing. And the second type of technique we learned is equivalence class testing. So this equivalence class testing is also about dividing the input space. And this time, instead of using the boundary values, we are using the equivalence classes of different inputs. And these equivalence classes are normally based on the characteristics of these inputs. And similar to boundary value testing, we also have two different types of characteristics. So we also have normal versus robust, which is about whether the values can be invalid or not, right? And we also have weak or strong equivalence class testing, which is about whether more than one parameter can take invalid values, right? So this is about equivalence class testing. And then we also learned another type of functional testing, which is called decision table based testing. So decision table is like a model that can model the cause and effect of a program, right? So the causes are actually the program inputs, and the effects are the actions or the behaviors of the program. So here are some key concepts in decision tables. So do you still remember what is a stub? What is an entry? So stubs are more like the table headers, right? And entries are the actual values of the table. And do you still remember actions and conditions? So actions are like the outputs of the program, and conditions are like the inputs we have, right? And we do have limited entry decision tables and extended entry decision tables. Do you still remember their differences? Like what's the difference between limited and extended? So limited entry decision tables means that each one of each one of the conditions there could either be true or false. But extended entry decision tables means can allow us to have entries which doesn't just take Boolean values, which can take numeric values or other types of values. So this is these are all the techniques we have learned for functional testing. And then we learn structural testing. So because functional testing is more like black box testing, and that's because we don't have access to the internals of the programs. And if we are given the source code of the program, then we can do white box testing. And the key about all these structural testing techniques or white box testing techniques is about the coverage metric we are going to use. So because we can have access to the source code, then we can collect code coverage, right? But talking about code coverage, there are different metrics here we can collect. And let's go through them one by one. And in this course, we are more focused on the coverage related to control flow graph. And I hope you can still remember what is a control flow graph, right? So, and there are some key concepts in the control flow graph, and let's go through them. So the most basic type of coverage we learned is statement coverage, right? So basically, normally a program is considered to be made up of a sequence of statements, right? So the target of most of our testings is to execute all the statements, right? So this is very straightforward. And we can also have branch coverage. So branch coverage are like the branches in the control flow graph. And branches are like the points where the control flow diverges, right? So for example, we can have those conditional statements like if, like switch, then after executing these conditional statements, the control flow of the program could diverge, right? It could either take the true branch or it could take the false branch. So the target of using these related to branch coverage is to execute all the branches. Basically, we want to cover all the not only all the basic blocks, but also all the edges connecting the basic blocks, right? So this is the basic idea of branch coverage. And then we also learned condition coverage. So condition, so just now we learned that, okay, branch is normally related to conditional statements, right? And conditional statements can have conditions inside these statements, right? And so it seems that condition coverage is very similar to branch coverage, right? But what is the difference here? So, like, what is the difference between condition coverage and branch coverage? So, which one is more more comprehensive, or which one contains which? Actually, condition coverage contains branch coverage because there are some conditions which are not used in conditional statements, right? We can assign Boolean values to some variables using some conditional expressions, right? So condition coverage is more comprehensive than branch coverage. And we also learned the MCDC coverage, which was used by some government agencies in the US, and it's actually used by NASA. And MCDC is basically to check the coverage of all the conditions, right? So that's about condition coverage. And we also learned the most detailed coverage we can get from a control flow graph, which is the path coverage. So path coverage is like execution path consisting of basic blocks and edges. And it's like a permutation of different basic blocks and different edges, right, on the control flow graph. So the target of edge coverage, of path coverage is also, of course, to try to cover all the paths on this control flow graph. However, there's a very, very infamous problem if we use path coverage, and this problem is called path explosion. So can you still remember what are the sources of path explosion? Like which types of code components could lead to path explosion? Which types of code components can lead to this kind of path explosion? Branches and loops. So for each branch, the number of paths will increase, will double the number, right? Times two, right? Every time we encounter a branch. And for loops, every time we get inside the loop, we get a new path, right? So branches and loops are the sources of path explosion. And therefore, because of this very infamous problem, normally we cannot achieve 100% of path coverage for most of the programs we are dealing with because they are just too complex. And in order to simplify the problem, we can have some other coverage metrics that are based on path coverage. So the first one is called boundary interior coverage, which is related to how many which is related to the internal values inside the loop. And we also learned loop boundary coverage, which is related to how many times do we enter a loop, right? And we also have LCSAJ, linear code sequences and jumps. And we can have different levels for this type of coverage. And if if we have level if we have level 1, then it means that we are not connecting any components. Then the coverage metric is kind of equal to statement coverage. And if we have level 2 LCSAJ, then it's more like a branch coverage, and so on. If we increase the level, we are getting closer to path coverage. And because of the path explosion problem, it's normally not possible to get 100% of path coverage. And then we also learned a little bit about data flow based coverage metrics, right? We learned diffuse pairs because using control flow graph coverage is not enough to reveal all the bugs. And we have practiced this with a question in assignment 1, right? So even if in the question in assignment 1, even if we can achieve 100% of path coverage, we can still inject some vulnerabilities which cannot be detected, right? So we need so path coverage is about whether we can reach certain part of the program. And the data flow is more about how did we reach this point? So with what values did we reach this point of the program? So that's why data flow actually provides a different angle of viewing the program states. And the key concept here we learned about data flow coverage is the diffuse pairs. So diff means a value is defined, and use means this value is used in some kind of operations, right? So this is all about the different types of coverage metrics we learned for structural testing. And then after this, what did we learn? We learned introduction, we learned black box, we learned white box. Then what did we learn next? We learned black, we learned white, and then we learned gray, right? Oh, sorry, we learned different levels. And for different levels of testing, it's more related to an old friend, the concept of software development life cycle, which is a very, very classic concept in software engineering. And for software development life cycle, if we combine it with the testing life cycle, we can have this very famous V model. So it actually shows us the relations between different stages of development and the different stages of testing. So for different levels of testing, the testing technique which are closest to the actual implementation of the code is unit testing, right? And then we can combine different units into some integrations. And then we can do system level of testing. And for unit testing, it's actually used for testing the actual implementation and the detailed design. And for integration testing, it's more about testing the architecture of the software. And for system testing, it's more about testing the software against the requirements, the actual requirements. And now let's go through these different levels of testing one by one. So for unit testing, normally it's done by the developers of the code. And it is actually the basis of test-driven development. So we can develop unit tests first, and then we write the code to pass these tests. And we also learned integration testing. So integration testing, the different variations of integration testing is all about how do we build these integrations, right? So how do we combine different units into some kind of integrations for us to test? So the first type of integration we learned is decomposition-based integration. So decomposition means we are decomposing the entire software according to some rules, right? So what we can do is we can given given a tree of the given a tree of the requirements of a program, what we can do is we can do top-down integration. So we can we can slice the program into different pieces according to the requirements, right? From top to down. And we can also do bottom-up integration. So which means that we are starting from the most detailed features, and then we try to combine them together to build up different integrations. And we can also combine top down and bottom up to do sandwich integration. And that is to find like something like a chain of features in the program. And we also have big bang integration, which is about just integrating everything together. And it is actually very, very similar to system testing. And that's about using the requirements to do the decomposition. And we can also try to use the code, the actual code of the program to do integration. So we learned the call graph-based integration techniques. And do you still remember what is a call graph? So is a call graph a control flow graph? Yes or no? A call graph is actually a special type of control flow graph. It's also about how the program executes, right? So in which order did the program execute? But instead of drawing the graph on basic block level, call graph is more about is on the function level. So it's about the calling relations between different functions. It's like which function is calling which one. And based on this call graph, we can do pairwise integration, which is about building integrations using pairs of callers and callees, right, on the call graph. And we can also have neighborhood integration. So neighborhood integration is there's a concept of the neighborhood size, right? Once we have decided the size of the neighborhood, then we can grab all the functions within the neighborhood in as the integration target we are going to test. So that's about call graph-based integration. And we also learn path-based integration, right? So we can integrate different parts of the program according to the execution path on the control flow graph. And the last level of testing we learned is system testing, which is to test the entire system as a whole. What we learned is there are different types of system testings. So the the most interesting one here is model-based testing, so which means that we can we can use some models to describe the behavior of the entire system, and then we can design test cases to trigger different behaviors of the model, right? And a typical model we have learned is actually the decision tables. And there are also some other types of models like the finite state machines, right? So that's about model-based testing. And we also learned some non-functional system testing, which are not related to the correctness of the program, but they can reflect other types of quality metrics. For example, we can do performance testing, which can check the execution speed of the system, right? Or the reaction time, response time of the system. And we can also do usability testing, which basically tests about whether a piece of software is usable or applicable for some scenarios, right? We can also do compatibility testing, which is related to testing about the compatibility between different components inside the software, right? Because now normally the software are made up of multiple different libraries, and there could be compatibility problems between different versions of libraries and dependencies. And we also learned several other types of non-functional testing. And then another important concept related to different levels of testing is called test scaffolding. So when we write test cases, this is like a complete structure for most of the unit tests we can write. So there are some key concepts here, like a driver, like a stub. So do you still remember the differences between drivers and stubs? Like drivers are basically the providing the context for us to execute the target unit, right? And stubs are more like some mockups for some unimplemented features, right? Or some features that we don't care when we do testing. So writing stubs is actually especially useful for test-driven development because we write tests even before we implement the target, right? So we need to mock up the features of the program properly. And for most of the testing, we also need to do the output comparison, which is to check whether the program encounters some bugs or not. And then we also need to do tear down, right? Which is related to releasing the resources we have used during testing, right? Or to reset the system state during testing. So we need to do all these when we write unit tests. And that's all the concepts we have learned for different levels of testing. And then we learned, um, then we combine the knowledge of the color of boxes and levels of testing to have gray box fuzzing. So gray box means it's the color of box, and fuzzing is actually a type of system testing technique. So when we learn when we learn fuzzing, we learned black box fuzzing first. So black box fuzzing, there are two types of black box fuzzing techniques. The first one is called mutation-based fuzzing. The second one is called generation-based fuzzing. So do you still remember the difference between these two types of techniques? Like why, like, are we using these two terms to, what is described by these two terms here? Like, are we describing the creation of test cases, or are we talking about the execution of the program or some other things? So what is described by these two terms here? So these two terms are actually used to describe how do we generate test cases. So mutation-based type fuzzing is more about given an initial seed, we are going to do some mutations. We are going to change the content of the seed to create new test cases, right? However, for generation-based fuzzing, we don't have seeds. Like we are creating new test cases from scratch. But but normally, how do we create test cases from scratch? We need to use some rules, right? We need to follow some models. Like for example, if we are testing a JSON parser, then we need to follow the rules to create JSON objects, right? So for generation-based testing, normally we need some rules or some models to guide the generation of test cases. And we also learned white box fuzzing. So white box fuzzing is normally related to symbolic execution and concolic execution. So so normally when we execute a program or when we run a program, it's considered as concrete execution because every value, if we stop the program at any state, then each of the value of the variables at that particular program state is a concrete value. But for symbolic execution, we can use symbols to represent the values of different variables instead of using the concrete values. And then we can accumulate the conditions of which are related to the input content, which acts as the constraints to the content of the input. And then we can apply some SMT solvers to find a solution that can satisfy all the constraints to reach a certain program state. And that is how symbolic execution works. And it actually requires us to accumulate constraints and apply a solver to solve these constraints. And for some very complex programs, there could be too many constraints which are not actually solvable by the solver. So normally, white box fuzzing or white box testing is not scalable enough to test large programs. So this is a drawback of white box fuzzing. And to combine the black box fuzzing and white box fuzzing together, we can have gray box fuzzing. So the key mechanism of gray box fuzzing is actually to divide and conquer, right? Gray box fuzzing is like we are still it's not black box, so we are still collecting information from the program, right? So like when you do assignment 2, you know that okay, we are collecting the coverage information of the executions, right? But we are not unlike white box testing. So white box testing requires us to know everything inside the program. Unlike white box testing, we only collect partial information from the execution. We only collect something like the edge coverage or some other interesting information which could be determined by us. So we don't collect all the runtime information. We only collect some interesting information. So this means that we can make the technique scalable for large programs. And the key mechanism is divide and conquer because we are keeping some, because we can collect feedback. So we know which test case is kind of better, right? For example, when we do coverage guided fuzzing, the Cs or the test cases that can bring us new coverage could be considered as the good ones, right? Then we can keep them and create new test cases based on these Cs. And in this way, we are kind of gradually exploring the program space, right? And we are kind of dividing the bigger problem into some smaller ones. So this is like why it is called a divide and conquer strategy here. And there are several different strategies used for gray box fuzzing. So the first one is seed prioritization. Because we have a list of seeds, we need to make the decision of which one to use next, right? So seed prioritization is related to the decision of which seed to be used next. And another strategy we learned is power. So this is after we do seed prioritization. So we know now we have the next seed to use. We need to decide how many new test cases to be generated with this seed, right? And this decision is related to the power scheduling strategy. And the last one is how do we generate new test inputs, right? We have decided how many new test inputs should we generate. Now we need to decide how do we generate them, right? And how do we generate them is related to how these mutation operators, right? We can design different mutation operators to create new test cases. And a very famous gray box fuzzer is called American Fuzzy Loop, and we learned some detailed mechanisms of it, and we are going to practice this with assignment 2, right? So that's all about gray box testing, and that's actually the first half of this term, and also the first half of today's lecture. Let's have a 5 minutes break. All right, let's start the second half. So actually in the first half of this term, we learned different testing techniques and which are the ones related to actually almost all of our assignment questions. And that's because I wanted actually to let you focus on the assignment during the second half of this term to give you more time. And so the second half of the term, we are covering several other concepts which are related to software testing, but may not be exactly new testing techniques. So the first concept we learn in the second half of the term is software complexity. So software complexity is useful for testing because because normally we assume that the more complex a piece of software is, the more likely it is to be buggy. So that's why we learn software complexity. And there are And just like coverage, there are different metrics for counting or for measuring software complexity. The first one is called unit level complexity. And we learned two different types of unit level complexity. The first one is cyclomatic complexity. So do you still remember what is cyclomatic complexity? So it is related to graphs, right? It is the number of edges minus the number of nodes plus 2, right? So we can, because programs could be represented as control flow graphs, so we can calculate cyclomatic complexity of a program based on the control flow graph. However, there's a there's a formula for doing quick or fast calculation for software, right? We don't need to draw a control flow graph for a very complex software or a very complex function to calculate the cyclomatic complexity. We can use the different statements and using the fast calculation formula to calculate this complexity here. And cyclomatic complexity is more related to the structure of the code. It doesn't really take into consideration the volume of the code, right? So a very long function with no branches can have a very low cyclomatic complexity, right? However, even if there's no branches in a very large sequential function, there could be some bugs inside that very big function, right? So we need to take into consideration the volume of the program or the size of the code. So that leads us to Halstead's matrix, so which is related to the number of total and unique operators and operands, right? There are several formulas to calculate this, but all of them are based on the number of unique operators and operands and the number of total operators and operands. So that's unit level complexity. And then we also learned integration level complexity. So because cyclomatic complexity is applicable to graphs, so for integration level of graph, what we can have is a cow graph, right? We can still use cyclomatic complexity here. And we also learned several metrics for calculating the complexity of object-oriented programs. So which are kind of related to different characteristics of the different concepts in OOP. And lastly, they are system level of complexity, but there's nothing much here. Like all of them are kind of covered by unit and integration. So there's no big difference between integration level of complexity and system level of complexity. So that's all about software complexity. And then we learned another important concept called test oracles. So test oracles are basically to tell us whether a test shall pass or fail. Because there are sometimes the bugs are easy to, this is related to the sensitivity characteristic of testing. So sometimes we can easily tell that a program runs into a bug, right? Because the program crashes, because the program misbehaves. That's very easy. But there are some cases where we can hardly tell whether a program runs into a bug. So that's why we need to design some test oracles to help us to tell whether the program is behaving normally or not. And there are different types of oracles here. So we can have specified oracles. So most of the specified oracles are manually created, and they could be model based. So for example, we can model the entire system as a finite state machine, and if the program runs into an error state of the finite state machine, then it means that the program runs into some bugs, right? And we can also use expected values as test oracles. These are just like the assertion, these values we used in the asserts of unit tests. And we can also do self-checks. So the difference between expected values and self-checks is that expected values are normally used in the unit tests we are writing. But instead of putting the assertions inside the test, we can add assertions in the logic of the original program, right? We can add some internal checks inside our program. So once something went wrong, it will give us an assertion fail. So these are the these are the different types of specified oracles. And then we also learned some derived oracles which could be obtained automatically. So the first one we learned is differential testing. So the basic idea of differential testing is to use two versions of two versions of programs implementing the same feature. For example, if we are testing, if we want to test some maybe some HTML renderer, for example, we can use, we can select our target from something like Edge, this Edge browser here, or Chrome, and see if an HTML page is rendered differently, right? If the result, like the rendering result is different, then it means that at least one of these implementations is wrong, right? So this is the basic idea of differential testing. So it is to differentiate between the outputs of implementations of the same feature. So this is the idea here. And we also learned regression testing, which is to use existing test cases to test the new features we are introducing during development. And we also learned the idea of expected values. Again, I think this is an error in this page. So we also learned metamorphic testing. So metamorphic testing is all about finding metamorphic relations that can capture the mechanism of the target we are testing. So sometimes it's hard to directly tell whether output is correct or not, but we can find some equivalence of the outputs, right? For example, we let's say we we want to test a function that calculates the value of pi, and we don't know the value of pi, so we can't check with the expected value here because we don't know the actual correct value of pi, right? So what we can do is we can use the knowledge that pi times the sine pi equals to sine x equals to sine pi cosine pi minus x. So a little bit of math here. So we know this. Then we can use the output of the function that calculates pi inside this formula and check if the formula holds or not. If this equation holds, then it means that the pi calculated by the function is probably right, right? And if this equation gets broken with the value we calculated, then it means that this implementation is definitely wrong. And that is the metamorphic relation here. So it's basically, the basic idea here is to find equivalence or some observations about the target we are testing. So that's the idea of metamorphic testing. And we also learned some implicit oracles. So implicit oracles are like the test oracles that are naturally that could be naturally derived from any program. Like for example, if a program crashes, then it means that there is definitely a bug, right? And to improve the sensitivity of these implicit oracles, we can use some sanitizers. And sanitizers are like some special type of instrumentations we can add into the programs during compilation. And one of the most famous sanitizer is called address sanitizer. It can help us to capture different memory related errors. And in the targets, in assignment 2, actually the targets we provided you are compiled with address sanitizers. So you can easily find bugs or crashes inside these targets. And lastly, we can use humans as oracles. So we can always ask a human to tell whether this program is running correctly or not, right? And these human oracles are especially useful nowadays because of these large language models. They are, during the training process, most of them are kind of using humans as feedbacks. So for doing for using humans as oracles, we can sometimes we can do crowdsourcing. So because this is very labor intensive, so we can use some crowdsourcing platforms to help us to distribute the tasks. So that's all about test oracles. And then we learned mutation testing. Mutation testing, although the name sounds like another testing technique, right? But it's actually a special type of technique. So can you still remember why it is special? So for most of the testing techniques we just learned, they are used to test the quality of the target program, right? But we don't know the quality of our test cases, right? We we can use test cases to test the quality of the software, but how do we know the quality of our test cases, right? So the the basic idea is very, very simple. So we can use test cases to evaluate programs, and we can also create programs to evaluate test cases, right? So the basic idea of mutation testing is to create some variations of programs that can help us to evaluate the test cases. And the way of creating these programs is through mutations. So through some random changes to the original program, which are likely to inject some bugs. And then we can use our test cases to see if our test cases can capture these injected bugs, right? And the key concept here, there are three key concepts here. So the first one is like the mutants. So the mutants are the program verification variations we have created, right, with some small bugs, small changes and bugs. And the process of killing mutants is to see if a mutant can pass our test or not, right? If a mutant cannot fails in at least one of the test cases, then it is considered as killed. And if a mutant can pass all the test cases we have, then this mutant is considered as a live mutant. And the mutation score is to use the number of killed mutants divided by the number of total mutants. So the more mutants we can kill with our test cases, the better the quality of the test cases are, right? So this is mutants. And we can use mutation operators to create mutants. We can use these mutation operators to simulate errors that could be made by the developers during development to create these variations of programs. And actually, these mutation operators determines the quality of the mutants, right? So the closer these mutants are to the actual errors in the programs, then the better the qualities of the mutants are. So mutation testing is different from mutation-based testing, and it is a special technique used for evaluating test suites. And near the end of this term, we learned when to stop testing. So when to stop testing determines the is determined is determined by the reliability of the program. So once we think that this software or this program is reliable, then we can stop testing. However, this means that we need to measure the reliability of the program, right? So we learned different metrics for measuring reliability. So reliability means the program can run without problem during the observed period of time. So so we are kind of like observing this program for a period of time, and during this observation, this program doesn't run into any problem, then this program is considered as reliable. So there are different metrics here for measuring reliability. The first one is the probability of failure on demand, which is related to the number of failed requests divided by the number of total requests, right? And availability is related to the on time and off time of the system, right? So sometimes the system is down, like for example, the server is down sometimes in USW, some of the systems. So that we can use the number of on time divided by the total amount of time units during this observed period as the availability of the software. And we can also use the rate of occurrence of fault, which is basically to count the frequency of errors during this observed period, right? And we can also calculate mean time between failures, which is related to the average amount of time we run the program before we encounter a failure of the program. And lastly, we introduced the concept of statistical testing, which could be used to measure these metrics, which is basically to simulate the real usage environment and we can collect like the usage profile of the users and then simulate how does this program run in this simulated environment and collect all the values for these metrics. So this is about when to stop testing. And then we learn a unique type of testing technique, which is considered as a which could be considered as either system level of testing or which could be considered as different all the three different levels of testings. And this is called combinatorial testing. So previously, all the testing techniques are dealing with the parameters of the program, but we somehow ignored the configurations that could be used by the programs, right? So combinatorial testing is more often used to test different combinations or different options passed to the program. And the key idea of combinations is to use T-way combinator, to use T-way combination. So because we can, if a program can take different options, there is a huge amount of permutations we can have, right, for the different combinations of these option values. T-way communication limits the number of combinations we can have. Like for example, for two-way communication, it means that we want to cover all the possible pairs of option values, right? So we don't need to care about the permutations involving three or more option values. We only care about all the possibilities for pairs. So this can limit the number of test cases needed. And do you still remember the optimal value of t for like most of the systems? Like what is roughly this number here? Like do we need to do four-way communications? Do we need to do three-way communications? Those combinations. So or two-way combinations. So for most of the systems, two or three is enough. Two or three is enough. And another thing is when we create test cases based on these T-way combinations, we don't need to create a test case for every combination because some test cases can cover multiple combinations, right? So how do we calculate the optimal set of test cases here? So the concept we use is called the covering array. So we use this covering array to keep track of which test case can cover which combinations. So we can minimize the test suite we have according to covering array. However, this covering array is hard or difficult to calculate. We have different algorithms, and we learned the greedy algorithm for calculating this covering array in this course. And talking about algorithms, we learned some advanced algorithms near the last week actually. So we learned some advanced algorithms that could be used for testing and some other related problems. So before we learn these algorithms, we tried to formulate testing as a search and optimization problem. So that the reason is if we can formulate testing as a search or optimization problem, then we can apply algorithms solving these type of problems to testing, right? So that's the rationale here. And sorry. So for search problem, so we are trying to search for a suitable test suite, right? So there could be an infinite number of test cases we can have for a particular program, and we are like searching the optimal set of test cases. So this is why testing could be considered as a searching problem. And for optimization problem, that is because we often have limited budgets, right? So we have some constraints when we do the search. So that's why we want to get an optimal solution rather than maybe the perfect solution here. So that's why by applying these constraints, we can further convert the searching problem into an optimization problem. And, and there are some algorithms for dealing with these optimization problems. And the first one we learned is adaptive random testing. So instead of creating the test cases purely randomly, what we can do is based on our previous testing results. For example, if a test case cannot find a bug, then we create a very different test case, right? So that's the basic idea of adaptive random testing. So if the previous test case is not good enough, then we just create a very, very different test case. So that's adaptive random testing. And we also, that adaptive random testing is considered as a heuristic-based algorithm, which means that it is based on some observations or some empirical findings, right? Based on some experience of humans. And however, we want to have a way to automatically extract heuristics, and this is called meta-heuristic. And we can have some meta-heuristic based algorithms. And genetic algorithm is one of them. So the basic idea of genetic algorithm is to simulate the evolution process of chromosomes and genes. So we can evolve the entire population through several generations and keep the good characteristics of these test cases or of these population and towards the optimized goal. That's genetic algorithm. And we also learned epsilon Grady algorithm. And this epsilon Grady algorithm is used for dealing with the multi-armed bandit problem. So multi-armed bandit problem is like we have multiple arms in a gambling machine. And by pulling each arm of the gambling machine, there is a chance for us to get a reward, right? And we have a limited number of tries for us to pull the arms. So how do we optimize our strategy to pull each arm, right? So that's a problem here. And we can use epsilon Grady algorithm to do this. And the basic idea is to have a small chance to try out a random arm and use a high chance to pull the arm which has been observed to give us the best result, right? So that's epsilon Grady algorithm. And thank you. That's all the concepts we have learned this term. That's everything we have learned. And I hope through this recap you can somehow recall what you have learned in the last 2 months. And you can see that actually you can explore this by dragging and moving around. And you can see there are some relations between each concepts here as well. So these relations can help you to better memorize these different concepts. And I hope that um, finishing all these assignments is not the end of this learning journey. And I hope you can continue to explore and try to keep these things in your mind. And that's it for today's lecture, and that's it for all the lectures this term. And thank you for attending today's lecture. Thank you.